Hello Year 10, this is the fifth and final topic of Year 10 Physics for Double Science. You can see here, as I'm ticking them off, all the topics you've done so far, and waves, or features of waves, is this final topic. So this is the front of your booklet. Please make sure you fill in your name, form, set and teacher. As usual, page 1 is what you would see in the inside front cover of your examination paper. It's two parts to it. You have the equations on the left and the SI multipliers on the right hand side, both for higher and foundation. Page 2 is for the close the gap feedback from your teachers. And we're going to start today on page 3. So if you could please at the top of page 3 write down lesson 1, excuse me, and the date, and the title is already underlined for you. Features of waves. And waves is really what we're going to be learning about. And you can see there, look, on this photo, surfer. Looks very familiar, surfer, actually. In the middle of a wave, I think surfers call them tubes. So it says underneath, this surfer has caught a wave. Draw a picture of what you think a wave or series of waves looks like. So let's get straight down to business. In that box there, I'd like you to draw what you think waves would look like. So pause the video, do it now. When you've done, press play. Now I think most people, when asked to do this, they will draw something similar to this. Because I think that's how most people would visualize waves. Now, if we were in classroom, I'd ask, did everyone draw a similar type of wave? Most people would have drawn that transverse wave. I'm coming back to that in a moment. This is the spec. I'll slowly go down it so you can, if you want to pause it at any point, you can. The spec, remember, is everything that you need to know or learn. And lesson 1 then, it is these A, B and C parts. And I'll just underline them. The difference between transverse and longitudinal waves. The description of a wave in terms of, these are new words for today, amplitude, wavelength, frequency and wave speed. And those things you see in brackets, that's lambda, that's a Greek letter, V and F are symbols for those quantities. We'll look at how we can represent waves, a graphical representation of transverse waves, including the labeling of wavelength and amplitude. Those are the 3 that we're going to be learning about today. So lesson 1 is from pages 3 through to 9. If you can now turn on to page 4. There's a chunk of text I'd like you to read through yourselves. So pause the video now and read through, press play when you've completed reading that paragraph. So that's a bit of information about how waves are used for surfing. Again, there's a few words we're going to be learning about in a moment: amplitude, frequency and wavelength. I'm just highlighting those as I'm speaking to you. But just to give you an idea of where this paragraph is talking about. Obviously surfing happens at sea, or I should say on the shoreline, and we live just off the M4, around about here. It's Pont de Lice, and of course there are surfing beaches dotted around Gower, near to us, and we do find that the best surfing beaches are down here, Llangennith, because of the way in which the waves come onto shore. And Newquay is down near Cornwall, and this is the coast look of Cornwall, and Newquay's here, so you can see that they'll also get those waves coming in from the southwesterly direction, which is often the prevailing wind in UK. What I'd like to do now is give you an explanation of amplitude, frequency and wavelength by just looking at a wave. Okay, this is a piece of software you can find on the internet, PHET Colorado, if you're interested, phet.colorado. Just Google that in and you can play around with this. It allows you just to pause, for example, so I just paused it there and play. And this little green button allows you to turn the dripping of the tap on and off. So you can see waves are created by some sort of vibration or oscillation, and in this case it's water dripping down onto the surface of a pond or a lake, whatever it is, and that's what creates these waves. Now, frequency and amplitude, if you look up the top right hand side, I can change the frequency. I'm going to take the frequency down to a minimum. Look what happens. I'm actually going to pause just let the water settle. So I've paused, no more drips, and you can see now the water will settle. Frequency are the number of waves produced per second. So if you've got a low frequency, you've got a low number of waves produced every second, just like this. And what I'm going to do now, I'm going to switch the tap off, let the water settle, and I want you to compare how that looks to when I increase the frequency up to a maximum. Watch. Okay, so we've got high frequency, a high number of waves per second. We measure frequency in units called hertz, and we'll look more at that in a moment. Okay, I've changed the frequency now to somewhere near the middle, and this time I'm going to change the amplitude. If you look at the top right, I'm just going to take the amplitude down to something quite small. Put the tap on. And you can see the drips are quite small. And the waves, the height of the waves are really small. Compare that to, just stop the drips for a second, when I put maximum amplitude in. Watch now. Big drip, lots of energy being introduced into the system, and the waves are much higher. Now what we can do, the way to measure the amplitude of a wave is to use something like a ruler, where we measure in distance. I'm going to pause a wave a second. I'm just pausing a wave there now. The amplitude of a wave can be measured if we take 2 points. So if we take those 2 points and I measure in between the two crosses 0.3 centimeters. Now you can see here that the amplitude is decreasing as the waves go along. When we're learning about waves, the amplitude will be remaining the same. So that's how we measure amplitude. It's the distance from midpoint to peak. Oh, I've just used a new word there. The peak is the top of the wave and the trough is the bottom of the wave. So they should be the same. You can see they're the same there. Okay. Another word for the peak is a crest of the wave. Now, the third word that I said we're going to talk about is something called a wavelength. And the wavelength is the distance between the peak of one wave and the peak of another. So you can see that's 2.6 centimeters. And we should find that 2.6 centimeters is the same at any point of those waves. Okay, so we've learned frequency, amplitude, and wavelength. And if we look at a different type of wave, a sound wave, and we look more on that in a moment, then we'll see the same thing. You've got, in this case, it's not a drip producing the waves in the air, it's the cone vibrating back and forth. And again, what we can do, if I pause that, the way in which we measure wavelength is if we go from the middle of one wave to the middle of the other, the wavelength there, look, is 142.9 centimeters. So the amplitude, frequency, wavelength. But before we do more on that, let's just summarize what we learned so far. Waves transfer something from one place to another. I did use this word a few moments ago, and the word's energy. And that's important to remember. Waves transfer energy from one place to another. When you were looking at the screen, it was going from left to right. That was a transfer of energy. Waves are a series of vibrations or oscillations. I mean, they go back and forth. Water waves make water molecules vibrate. That's a bit of a tough one for you to answer. We'll go back and look at the software we were just using. The water molecules are vibrating up and down, whereas the wave direction is going from left to right as you're looking at it. So the water molecules are vibrating 90 degrees or perpendicular to the wave direction. Don't worry if you don't get that straight away. So the water wave make water molecules vibrate perpendicular. Remember, that means right angles. Perpendicular to the wave direction. Now, again, what I mean by that is, if here are your water waves moving from left to right, the actual particles themselves are vibrating up and down that way. In our atmosphere, sound waves make air particles vibrate from side to side, or something that we will be learning about if we look at sound waves again, and we look at it in terms of particles. Each one of those little circles white or red, if you look at them, they are vibrating away from the loudspeaker, the cone. When we say they're vibrating parallel to the direction of the wave. Now, to understand that a little better, we're going to consider two types of waves that you need to understand. Number one, longitudinal waves, and number two, transverse waves. So the first one, longitudinal waves. So these are like our sound waves we were just looking at. And what we find is that we get areas of compressions and rarefactions. Let's look back at this again. If I were to pause that, what you'll notice is there's areas where the particles are very close together or compressed together. That's what they call compressions. And areas where there's almost an absence of particles called rarefactions. If I move this little tape measure, right, as almost use it as a cursor. So the tape measure at the moment, what I'm moving it about, would be in the middle of a compression. A rarefaction here, in between a compression, or in between two adjacent compressions. Compression again, rarefaction. We're going to look at a slinky spring and see the same thing. So what we get as areas of compression, I'll highlight here in yellow. There's another one there. There's another one there. And in between, and I'll highlight them in a different color, I'll just use green, and in between the compressions, you can see where the slinky springs, or the adjacent slinky springs, are spread out, called rarefactions. We'll look at a quick video now to see how that works in reality. Okay, now when we look at this, you can see what's happening is that, I'm just going to pause that a second, is that the hand on the left of the screen, I'll just draw a little arrow here, is moving to the left and to the right. And what you can see is a compression moving from left to right. And there's a little string attached to the spring on the right hand side of the screen that's moving left to right. It's not up and down. It's moving in the same direction as the hand, left to right. Watch again. Right. So watch again now, as you can see that compression moving down. Watch how the wave travels and also how the hand is moving. We say the wave direction is the same as the vibration direction. Now what we say is, in a longitudinal wave, I'll make some notes on the right hand side, the particles vibrate parallel to the wave direction. So the wave direction is from left to right. Look at the video. You can see that bit of blue string that's been put on the spring itself, left to right. And the question they're asking there, how does the ribbon move, left to right? What can you conclude from this? Well, the particles are moving from left to right. And we say in a longitudinal wave, longitudinal wave. Particles travel parallel to the wave direction. So that's the first type of wave. What you need to do now is make your own notes on longitudinal wave. I'll verbally read out what should be included. So, and I'll write down some keywords as well, but you write it down in your own words to make sense of it. Right. So you'd say longitudinal waves are created when the vibration of the waves vibrate perpendicular to the wave direction. Compressions and rarefactions are created in the wave. Let's now look at the second type of wave, transverse waves. And I'm going to make a few notes on the right of the video as we watch it. This time, what we're going to see is that the particles vibrate up and down. So that's the movement of particles. And the wave direction is left to right. So can you see if the movement is that way and the wave direction is that way, then we say they are perpendicular to each other. Compare to the longitudinal waves. Longitudinal wave particles travel parallel to the wave direction. These are the two key words then. Parallel for longitudinal and perpendicular for transverse.
Okay, that's a bit better. Yes, that's better.
这么 standing wave，
这个要差不多要standing了。
It's almost a standing wave already.
Yeah. Not quite a standing wave lah, still moving.
How does the hand move? Up and down. How do the waves move? Left to right.
Okay, quite clear lah. Okay. Actually, this is good. You know why? Because the ribbon seems to come back to its original position.
The direction is from the hand to us. So again, perpendicular. Look at the yellow spot. I like this slow-mo. You can see the wave moving along. And look at the yellow spot. It's starting to move now to the left. The yellow spot moved to the left, then it moved to the right, whereas the wave direction was perpendicular to it. So in summary, if we look at the two types of waves, the first type we looked at was a transverse wave, vibrations 90 degrees to the direction of travel. The longitudinal wave has vibrations parallel to the direction of travel. So transverse at the top. Keywords again, transverse wave, vibrations 90 degrees. Remember, you can use perpendicular, instead of 90 degrees. And for longitudinal waves, vibrations are parallel to the direction of travel. You need to learn and remember that. So what I'd like you to do now is complete this section here for transverse waves, saying something similar to what we just looked at in transverse waves. The particles vibrate at 90 degrees to the direction of wave motion. So you write that in here. What I'd like you to do then is just add underneath an example of both a transverse wave and a longitudinal wave. So at the bottom, example for a longitudinal wave, sound waves, and for transverse waves, light waves, water waves. I suppose what we could add to both, we just looked at them, slinky springs. So let's pluralize that to examples and add in slinky springs. Right, turn over now please to page 6. So what page 6 should look like. And your task here is to complete this Venn diagram. Remember, the way Venn diagrams work is that everything just in this section in green here would be applicable to longitudinal waves only. Everything over here would be applicable to transverse waves only, and everything in the middle would be applicable to both. Okay, so pause the video now and press play when you've added in as much as you can. I'll give you a quick starter then. So longitudinal waves, they have compressions, and transverse waves have peaks. Yeah. You can carry on now and press play when you're done. Okay. You can add parts from the completed Venn diagram here to yours if you so wish. There's nothing new there to what we've already covered, so I'm not going to talk through that. That's just a quick recap of what you should have learned so far, and you can pause that and add to your notes as you wish. So if you move on now please to page 7, and we're going to learn more about these 4 key terms: wavelength, amplitude, frequency and wave speed. We've covered the first 3 already, we haven't covered the 4th, wave speed. It says in the next diagram we shall focus on the first 2 of these, that's wavelength and amplitude. What do you need to do is, it says, vary the shape of one wavelength using a highlighter or different coloured pencil. What I'd like you to do is label the top wave diagram, then I'm going to ask you to draw out your own wave on the bottom diagram. So the first diagram here, there are 4 arrows, 2 going horizontally and 2 vertically. Let's highlight those first. So the 2 then that are shown horizontally show the wavelength. So let's label that wavelength, and the symbol we use is a Greek letter lambda, and in this case we can measure and I want you to measure with the ruler the size of this wavelength. Now, my ruler is going to be different than yours, but you might be able to work out, and I'll put some little marks where I'll just bring it down slightly. Okay, so I'm going to be using this point here as 0. That's 1 centimeter, 2 centimeters, 3 centimeters, 4 centimeters, 4.1, 2, 3, 4, 5, 6. 4.6 centimeters. In your booklets, you'll have a different reading. But what you'll notice is, if you do the same down here, and we make the same measurements, it should also be 4.6. Let's just do that. So here's 0. Let's just make sure we've got this in the right place. There we go. There's 0. Then we've got 1, 2, 3, 4.1, 2, 3, 4, 5, 6. Okay, so we can label this wavelength lambda equals 4.6 centimeters. Now, in fact, you could do that at any two similar points on the wave. So you could take from this point here to that point there, and again that would read 4.6. Or if you could go from the bottom to the bottom of the next wave, that would also 4.6. So the wavelength is the distance from adjacent peaks, or adjacent, we call these midpoints. The two vertical arrows here measure the amplitude. So the amplitude is the distance from the midpoint to the peak of a wave, or midpoint to the trough of a wave. And again, they should be the same. Let's get the ruler. And okay, that's 0. That's 1, just there. That's 2, 2.1. 2.1 centimeters. And we could do the same down here. There's 1, there's 2, 2.1 centimeters. What I'd like you to do now is, in the second diagram, draw a wave with a wavelength of, and I'll write it over here on the right hand side, with a wavelength of 2.3 centimeters. So that's half the wavelength. And we'll go an amplitude. We'll keep the amplitude the same, 2.1 centimeters. Well, I'm going to help you do just that. We're going to start at the same point, so we'll put a cross there. But if you look at one wave, and I'll highlight that for you now at the top. And so I'm highlighting in green here what one whole wave looks like. That's I've done a quarter of a wave there so far. I've highlighted a quarter of a wave. Now I'm down to half, 3/4, 1. So what I need to show is that I'll be completing the midpoint here because we've got half the wavelength, is now going to be here. That's 2.3 centimeters. And in between, we'll have another point there where it crosses that rest position. And then we're going to have a peak there and a peak there. And that would continue across the graph. So the amplitude's the same and the wavelength is half. So what we can show now is that the wavelength here is 2.3 centimeters. You can just about make that out. If I bring that down slightly, there's 0, there's 1 centimeter, there's 2 centimeters, and that's 2.3 centimeters. If I just continue now, using my green pen, I think this is the easiest way to draw waves. If we just put crosses at the midpoints, or the peaks and the troughs, it just makes things a lot easier. And just join them up. Try and make sure that you do use that characteristic curved shape when you're drawing your waves. So, what is a wavelength in millimeters? We're talking here now about the top wave. Well, we worked it out to be the wavelength is 4.6 centimeters, so that's 46 millimeters. How many waves are in one diagram? Okay, one wave, let's use a highlighter. That's a quarter of a wave. That's half a wave. That's 3/4 down to here. And that's one whole wave. Up to here, let me explain that. If you look at this spot here and this spot here, they're identical. It's the start of a new wave. So that's quarter of a wave, and that's 1.5 waves. I could do that in a different colour just to make it stand out. I'll do the next second wave in purple. So that purple now is the second wave, 1.25, 1.5. 1.5 waves. Moving on now then to page 8. This is a quick activity for you to do. I'm going to write 4 words on the right hand side, and then you've got to put them in the correct places here. And these are the 4 words or phrases that you've got to use. Wave speed's one of them. Frequency is another. Amplitude and wavelength. Wavelength, amplitude, frequency. You've got to write them in on the left hand side. So you pause the video now, you write them in, and then I'll go through the correct answers with you in a moment. Okay, should look like that. Take them if you're right, correct them if they're wrong. Then, underneath, starting on page 8, moving on to page 9. There are 6 questions for you to do. Again, this is going to be a self-assessment task. Pause the video now, answer these in your booklets, and we'll go through them together when you press play again. Okay, the first question then, label up the wavelength on this wave trace diagram. Using a ruler, you could have labelled from peak to peak or trough to trough. So if I were to go peak to peak, I could do that, or I could do trough to trough down here. It doesn't matter. Now, obviously, the values that I'm going to be using will be different to the ones in your box. So wavelength, I'm going to use the symbol lambda equals 1.2, 1.1, 1.2, 1.3, 1.4, 1.5, 1.6 centimeters. So label up the wavelength on this wave trace diagram. Yeah, done. The wavelength was 1.6 centimeters or 16 millimeters. Label up the amplitude on the wave trace diagram. So the amplitude, again, you can choose any one of these points here. I'm going to choose this one. And it's from peak to midpoint. And I'm going to use the symbol A equals I'm just changing that back because the scale will be changed. Equals, so I'm just using, again, U will be different in your booklet. 1 centimeter, 2.1, 2, 3, 4, 5, 6, 2.6 centimeters. Okay. So if it's 2.6 centimeters for the amplitude, that's 26 millimeters. How many waves are present in this wave trace? Remember, this is the one I got wrong last time, so we're going to take our time with this and do it together. I'm just going to use a highlighter, a little thicker. Okay, so that's a quarter, that's a half, 3/4, 1. That's 1. 2, 3, 3.5. Now you haven't got to highlight it as I just done there. You could do it another way. If you spot that that's the start of one, that's the start of the next one, so that's 1 wave. Oh, again I've made a mistake. Look. 1, 2, 3, 3.5. 3.5 waves. What type of wave does this trace show? And give an example. So it's a transverse wave. An example would be a water wave. You could also write down a light wave or slinky spring or string even. Give yourself then a mark out of 9. Use descriptive words to compare the keywords for both waves. And I've added now and measure the wavelength and amplitude for both waves. we're going to work on the basis that each one of these squares is 1 centimeter. 1 centimeter in both directions. A couple of other things. Oh, there's a slight typo there. That's lambda. Lambda should be shown like that. It's just been reversed, that's all. So you can correct that. Before we do this though, I'm going to introduce pitch and volume. I'm going to just show you what that means. The wavelength there is around about 147.3 centimeters. If I take the frequency you can see the wavelength down to about 78. So high pitch means high frequency. Notice I hadn't changed the amplitude at all, so I'm going to leave that sound, put that sound back on now. Its volume, the lower the amplitude, the lower the volume. Higher the amplitude, so move the amplitude back up. You can probably see that better by looking at particles. If I reduce the amplitude, the particles in the air aren't going to move as much. In fact, now zero amplitude, the particles in the air are just vibrating very, very slightly, but there's no pattern. Okay, I'm going to start there for the wavelength, so you can see that the wave D has got a wavelength of 4 centimeters. That'll be the same in your booklet because we're just working off that reference grid. So it's got a longer wavelength than wave K. I'd like you to do as much as you can now for amplitude, frequency, pitch and volume. So you need to compare the two. Okay, I've just completed that. For amplitude, the amplitude here look was 2 centimeters or 1 centimeter. So we say that wave D is a larger amplitude than K. The frequency, well, because there's more waves in K, we say it's got a higher frequency than D. And it's also therefore got a higher pitch. Just think of the quick simulation we looked at. And volume is linked to amplitude. So the larger the volume, so the larger the amplitude, the higher the volume. Okay, well that's it for this first lesson. Make sure you complete the plenary assessment and see you next time. Bye for now.